everybody. In this video, we're going to talk about complex eigenvalues. So far, we've seen some real valued eigenvalues. Now we're going to see some complex eigenvalues and how they are related to symmetric and skew symmetric matrices. So let's begin this video with a definition. So we're going to say if X is a vector in Cn. So Cn is our complex plane. And it's going to have n tuples, just like Rn would, but now they're complex values. Then X bar. So if you're able to type a vector, you can use like a boldface for your vector, and then you would just have a boldface with a bar over it. But I can't write very easily bold on a board. So I'm going to write X bar for the vector with a bar over it. Okay, that's what we're defining. This is the vector. With each entry replaced with its complex conjugate. So for example, so we can see what one of these things is going to look like. If X is a 3x1 vector, we've got 3 minus I, 2, and 5i, then its conjugate is going to be 3 plus I, 2, and negative 5i. So remember, the complex conjugate of a complex number keeps the real part the same, but negates the imaginary component. So 3 minus I has a complex conjugate of 3 plus I. 2 is a real number, so it doesn't change for the conjugate. And 5i is purely imaginary. It has no real component. So this is going to turn into a negative 5i. So we will be using the words complex number and imaginary to mean what they mean. They do mean different things. A complex number is composed of a real part, so in this case, like the 3, and an imaginary part, the piece that has the I. So when we say purely imaginary, we mean the real part is 0. So we're going to mean that we have something like 5i. And when we say we have a complex number, it could be real plus imaginary, purely real, or purely imaginary. So all 3 of these numbers are complex. This one is purely real. This one is purely imaginary. So we're going to have a theorem to go along with this. So this is theorem 26. And it says if A, and this is going to equal Aij, is a symmetric n by n matrix, and X and Y are real vectors, in Rn, then if I take A times X and I dot it with Y, that's going to be the same as X dotted with A times Y. So we have this relationship with different vectors and how we can manipulate them with the dot product. One thing to bear in mind is that you have to keep track of dimensions when you're doing matrix multiplication. So I can't do X times A, because X is going to be, n by 1, and A is going to be n by n. So over here, you'll notice, right? I can't do like X dot A, I can only do X dot a vector. So that's why we're going to have to multiply Y, the vector Y, by that matrix A first, and then we'll have 2 column vectors that we can then dot. Similarly here, I can't have X times A first because the dimensions won't work. So we'll have A times that vector of X, and then we will dot that with Y. All right, and then I've got two more theorems about symmetric and skew symmetric matrices. So I'm just going to pull those up and share screen so we can look at those in some detail. Alrighty, so our first theorem here, theorem 27, is about symmetric matrices. So if A is a symmetric matrix, then its eigenvalues are guaranteed to be real numbers, and the eigenvectors that correspond to those eigenvalues are going to be orthogonal. So what that means is if you have a symmetric matrix, you know that when you go to find the eigenvalues, you're not going to get any, complex numbers that have imaginary components. You're just going to get real values for that. If you have a skew symmetric matrix, the opposite happens. So if you have a skew symmetric matrix, then the eigenvalues are going to either be 0 or they're going to be purely imaginary. So they're going to be complex numbers that have no real part unless they're 0. So that's what theorem 28 is saying. So let's do an example together on the board of practicing this, I guess. So we will, we've got two matrices over here that we're going to find the eigenvalues for. So the first one is a skew symmetric matrix, right? So if we reflect across the main diagonal, we get the same value, just opposite signs. So for a skew symmetric matrix, we're going to expect to get eigenvalues that are either 0 or purely imaginary. That's theorem 28. And this matrix B is a symmetric matrix. It's tinier, but if I reflect it along the main diagonal, I get the same thing. So A is A transpose. So this is going to be our symmetric matrix. So we're going to expect to get purely real eigenvalues for that matrix. So let's get the bigger one out of the way and see what we get. So to find the eigenvalues, remember you need to find the determinant of xi minus a, and we're going to set that equal to 0. So when we do this, we're going to do x minus each of the diagonal components and negate everything else. So this is going to become x -2, 1, 2, x -1, -1, 1, and x. And we're going to find the determinant of that matrix and set it equal to 0. So in order to find the determinant, you can expand along any of these rows or columns. I'm going to expand along the top row just because I had to pick some place to go, right? So we're going to start out with x times the determinant of this 2 by 2 matrix. So that's going to be x squared plus 1. Then since this is positive, we're going to get a negative. So we have negative, -2. It's going to be plus 2. Get rid of, the first row and the second column, and we're going to get 2x minus 1. And then positive, negative, positive. So we're going to get plus 1 times the determinant of this 2 by 2 matrix, which is going to be 2 plus x. And that's all equal to 0. So now it's just a matter of algebraic simplification. So let's just distribute all of this and see what we get. So I'm going to get x cubed plus x plus 4x minus 2 plus 2 plus x. That's going to equal 0. And it looks like when I start to combine things, obviously there's only one x cubed component. We have no x squareds. And then we have 1 and 4 is 5, plus 1 makes 6x. And then -2 plus 2 cancel each other out. And then we can factor this, right? So we're going to get x times x squared plus 6 is equal to 0. Now, if this had been x squared minus 6, we would do x plus root 6, x minus root 6. But since it's positive, we're going to get imaginary things. So we're going to get x plus I root 6 and x minus I root 6. And you can check when we multiply this, we will in fact get 6 from that, or plus 6. So this means we've got our 3 factors. So our 3 eigenvalues from the first factor, lambda 1 is going to be 0. Lambda 2 is going to be from here a negative I root 6. And from here, lambda 3 is going to be a positive I root 6. So what we see when we get these eigenvalues is that we have one eigenvalue that is 0, and then we have two eigenvalues that are purely imaginary. And this is what theorem 28 was saying we would get. Since we have a skew symmetric matrix, these eigenvalues fit the classification that we would expect from it. So let's do the same thing for matrix B now. So we're going to do the determinant of xi minus b, equal that to 0, and then find our eigenvalues that way. So let's work that out over here. I think I have enough space. So we're going to do the determinant of x minus 1, negative 1, negative 1, x plus 2. This has to equal 0. So I can multiply those two. I'm going to do my distribution as I multiply, and I'm going to move it down a little because I have more space in through here. So when I multiply this, I'm going to get x squared plus x minus 2. So that's again x minus 1 times x plus 2. And then I have to subtract 1 from this component. So we end up with x squared plus x minus 3 equaling 0. Now, in this case, excuse me, in this case, this is not going to factor. So we can either complete the square or we can use the old stand by the quadratic formula. That's the approach I'm going to take. So we have x is equal to negative b, so negative 1, plus or minus the square root of b squared, which is 1, minus 4ac. So negative 4 times 1 times negative 3 is going to give me plus 12, all over 2a, which is just 2. So this means that our eigenvalues are going to be negative 1 plus or minus root 13 all over 2. So in this case, we get two real, purely real eigenvalues. One of them is where we add the square root of 13, and the other one is where we subtract it. Notice that we didn't get any negative values under the radical, so that's why we don't get anything that is imaginary or imaginary component to this. So this example is confirming what theorem 27 said we would get. We started out with a symmetric matrix, and we ended up with purely real eigenvalues. Now, I'm not going to make us find the eigenvectors when we have these gorgeous complex eigenvalues right now, but just to kind of see that this is the effect that we would end up having. So that's going to wrap it up for this video. Our next video is going to be the last video of the semester of the course. So bring your tissues, don't miss us too much. In that video, we're going to be talking about not just diagonalizable matrices. So we're going to bring back diagonalizable matrices, but they're going to be orthogonally diagonalizable, which means we're going to be able to diagonalize the matrix using orthogonal matrices P, not just any old invertible matrix P. So make sure you have your coffee in hand for that one, and I will see you in that next video. In the meantime, I hope you have a wonderful day. Bye.